So I welcome everyone for the boot camp. So this is basically a knowledge sharing sessions. So today we are going to share about a little bit about the battery thermal management systems. So let me share my screen. Okay, is my screen visible, Balaji?
Yes.
Yeah, thank you. Thanks a lot. Uh, okay, so for the coming 45 minutes, we're going to discuss about the battery thermal management systems. What are the design approach for cooling technologies. So we know that the electric vehicle is the emerging field. Nowadays, we're going to discuss about the basic on battery, where battery is the heart of the electric vehicles. And here, yeah. So these are the things that we are going to cover in coming 45 minutes. So why electric vehicle? What is the need of electric vehicle? And what is my battery? And what is my thermal runaway? What is my BTMS systems? Like battery thermal management systems. And I'm going to share one of the case studies used for battery thermal management systems. And here, before starting the sessions, you can see this picture. Why are e-scooters in India catching fire? So take few minutes and answer for my questions. You might recently see it in the news or might have observed in newspapers or televisions. A lot of e-scooters are catching a fire. In past 1 year, you can see a lot of scooters. May I know the reason for this? You can put it in your chat box. Yes, overheating of battery.
Dr. Jitesh.
Yes.
Just sorry to interrupt. So guys, I can see a lot of people are answering me directly in the chat. So it will be great if you can direct message to Dr. Jitesh, right? So you can basically select from the wherever you're chatting, there is a tool, right? So you can basically click on the drop down and you can select Dr. P Jitesh, right? And you can directly answer it to him, right? Or if you have any technical questions, you can directly ask to him. So at the end, we can basically take those questions. But for answering, at least you should answer to Dr. Jitesh so that he can take a look at your answers, right? So don't message me or Balaji. I can still see Mohit. You are direct messaging me, right? Muralidharan, Mohit, please direct message to Mr. Jitesh. Okay. So there is a drop down. You have to click on that and select Dr. Jitesh and answer it to them. Okay. And guys, last thing, this PPT will not be shared with you guys. Okay. We will be uploading the recording of the entire session on YouTube in 2 weeks of time. So you can, you will get the access to it, if you are basically subscribing to our YouTube channel, but this PPT will not be shared. So I hope I have answered that question. So yeah, so Chandan, again, you are answering me. Sudeep, don't answer me, and answer it to Jitesh. So workshop has already started, Sudeep. So yeah, over to you, Jitesh. Thank you.
Yeah, thank you. Okay, thanks for answers. I can see a lot of answers like overheating of battery, no proper thermal management issues with battery due to overheating, rise in temperature. Great, very good observations. So due to heat of battery explodes for battery quality, improper cooling, they did not optimize for it, overcharged because of overheating, exposure to sunlight. Okay, poor heat transfer, heating effect. So a lot of answers are relevant to the overheating and short circuit, coil capacity, improper thermal management. Great guys, very good observations. Yes, exactly. The thermal management, the overheating of batteries during the charging and discharging leads to the thermal runaway, which captures the fire in the battery systems. So in last 5 years, you can see the lot of industries in the field of electric vehicle have been emerged, and without there is no proper R&D, they have released a lot of scooters. So we are getting some like the lot of batteries catching a fire due to the overheating during charging and discharging. And here, great answers, guys. Now let us see why we are using electric vehicle. Why the electric vehicle is in hot in last 5 years? Now, here the main reason for electric vehicle is the two things. One is with respect to the environmental pollution, and second thing is with respect to the energy demand and availability of the fossil fuels keeps on decreasing. The environmental pollution is the major concerns. You can see since nowadays where most of the vehicles are run by the four-stroke engines, which is where the petrol and the diesel or some other fuels are the major source for running the IC engines. So which leads to the emissions. So you can see a lot of emissions emitting in the IC engines, so which leads to environmental pollutions, where these emissions constitute of lot of combustion like NOx, CO2 particles, and soot particles, so which leads to the environmental pollutions and also energy scarcity. You can see there is a lot of energy demand in terms of fossil fuels. So more the energy demand and the availability of fossil fuels keeps on decreasing, depleting. That's why we are going to switching the IC engine to the electric vehicle sector. But however, even for the electric vehicle, we need some power. This power is generated by the power plant, maybe thermal power plant or some other power plant, which is located away from the city. And even it leads to the pollutions. But in this case, we can avoid the city pollutions. We're just focusing on we are shifting from the bulk pollution to the single point, focus point pollutions. But of course, if you want to reduce the environmental pollutions, we have to switch from the non-renewable to renewable sectors by using a wind power station or solar power stations, so that we can reduce the environmental pollutions. So this is a step-by-step procedure. First, we are switching to electric vehicles. Maybe in future, everyone is using the solar panels for power productions. Now, these are the basic major components of the electric vehicle. You can see there is an electric motor, and you can see motor drive and battery converter. So basically, we use the AC power to charge the battery, which is need to be converted to DC power. And we have onboard charger and auxiliary battery to start the engine, and some transmissions for battery to the electric motor. And the major thing is a battery bank. So this battery bank is the heart of the electric vehicle. Okay, which almost consists of 30% weight of the total vehicle, or even 30% of the whole size, even the two-wheelers or four-wheelers. So battery is the heart of the electric vehicles. Not only in the electric vehicle, even can use this. We are using this battery bank in the hybrid electric vehicles, where we have both engines and the battery bank. Now, so since the battery is the major, the heart of the electric vehicle, now we are going to discuss about battery. And there are different types of batteries available in the market. Like previously, we are using the solid state batteries. Nowadays, we are using the lead acid batteries, like nickel cadmium, nickel metal hydrides batteries, lithium ion, and plastic lithium ion. And nowadays, we have also lithium ion metals, and which is unsafe. It leads to explosion some days, and it not has very good rechargeability. So most of the case, we are using lithium ion batteries. Even like there are a lot of batteries like lithium ferrophosphate, and also there are a lot of batteries in under research like aluminum, zinc, tungsten materials. The lot of batteries are in the progress research. So maybe in future we'll get a lot of batteries, but now we are using the lithium ion batteries in the every electric vehicle. Not only two-wheelers, we are also using the four-wheeler. And also, if you compare from this graph, the X scale shows the energy density in terms of watt per kilogram, which defines lighter weight. And in the vertical scale, it denotes the energy density in watts per watt hour per liters, which decides the small in size. So if you take an example, lithium, why it is lighter in weight and smaller in size compared to other batteries. So lithium ion batteries, the most commonly used batteries in the electric vehicles. Now let us see the principles of the working principle of the lithium battery. So basically the lithium ion battery consists of the components like anode and a cathode. So basically the anode is made up of the carbon family. Mostly we use graphite, and the cathode is made up of the lithium metals, lithium metal oxide like lithium magnesium oxide, lithium cobalt oxide, lithium chloride oxide. There are a lot of lithium metal oxides used here for the cathode side. And there is a thin membrane which separates the anode and the cathode part, which is made up of the plastic membrane. This is a kind of plastic family which separates the cathode and the anode electrode. And this cathode and anode electrode is submerged in the electrolyte. Basically, this is a lithium salt solution. The electrolyte is lithium salt solutions. And during the charging, the ion will be transferred from between the cathode and anode, and the electrons will transfer from the cathode to anode. You can see this is the circuit of the charging port, where the electrons will basically transfer from the cathode to the anode electrode, and in discharging it is a reverse manner, where the electrons will transfer from the discharge from the anode to the cathode. And within the chemistry, within the battery pack, the ions will be the lithium ions will be transferred between the cathode and the anode. And this is the basic principle of the lithium batteries. And the right hand side, you can see the cut sectional view of the cylindrical batteries. So this is your cut sectional view of the cylindrical batteries, where you can see. Okay. Yeah. So where you can see the cut section view of the cylindrical batteries, which consist of the positive electrode and the negative electrode, and there is a separator. So basically, this separator is a thin membrane. Okay, this is thin plastic membrane, which is made up of a plastic family. And in addition, apart from this, this second, guys. Okay. Hey, Balaji, am I audible?
Yes, sir. Yes, sir. You're
Yeah,
audible.
sorry, I think.
Yeah, it's okay.
Is my screen is visible?
Yes, sir.
Yeah. 1 second. Let me share my screen. Yeah. So here, the right hand side, you can see the cut sectional view of the cylindrical batteries. So the cylindrical batteries are most commonly used batteries, and in addition to the cylindrical batteries, we have a lot of the like lot of shaped structures. Like we have prismatic batteries, we have the coin-shaped batteries, and even we have the pouch type of batteries which is used in the mobile phones. And based on the applications, we have different structures like cylindrical, prismatic batteries, and pouch batteries, coin-based batteries. Now let us see what's been cell, module, and pack. So basically, in the electric vehicle, we have the battery pack systems. So what does this mean by battery pack systems? So this is called a cell. Okay, this is cell, which is called the single unit device, which stores the energy in the form of chemical energy, and which delivers in the form of electrical energy is called as cell. And a collection of cell is called as a module. Okay, a collection of cell which may be connected in the series or parallel, or both series and parallel, which is called as a module. And we have then what is the pack? A series of a module, a collection of modules is called as battery pack systems. And this battery pack systems are commonly used in the electric vehicles, like maybe 2-wheelers or in 4 wheels. This is the difference between a cell, module, and pack. So collection of cell is called as module. A collection of modules is called a battery pack systems. Okay. Now let us see battery connected in series and parallel. So now, in this case, we can see the battery which is connected in series and in parallel. So here the battery in parallel connection in the sense, second. Yeah. So basically batteries are connected in both in series and parallel. When I say in series connection, these volts are multiplied. Here in this case, you can see that 3 batteries are connected in series. That means here each battery is having specification of 3.4 H, which is called amps hour, or 3400 milliamps hour, and voltage of 4.2 volts. When the batteries are connected in series, basically the voltage will be multiplied. So in this case, we can see 4.2 into 3, which is 12.6 volts, and it has the amps rating of 3.4 amps hour. And here in this right hand side, you can see the batteries are connected in parallel, which means the amps ratings are getting multiplied. Now in this case, 6 batteries are connected in parallel connections. So here, which is 3.4 AH multiplied by 6, which is almost 20.4 AH or 20,400 mAh, where mAh means milliamps hour. So this total battery pack system has in specification of 4.2 volt and 20,400 mAh. So basically the batteries are connected in series and parallel based on the application, load application point of view. So if the load is having the specification of 12 volt, then you have to connect a battery in series. So which will give the 12 volts. If we 3 batteries will get 12.6 volt for this specification. So most of the application we need both the voltage and the amps rating. So in such cases, what we can do is we can connect batteries both parallel and in series connection. So in this case, you can see the batteries are connected both in parallel and series. In the previous case, this is called parallel connection. 6 batteries are connected in parallel, and here 6 cross 3. So 6 batteries connected in parallel, and this is called a single module, and this module is connected in series, 3 series. So basically the voltage is multiplied of 3 times and amps rating is multiplied in terms of 6 times. So which gives the total specification of 12.6 volt and 20.4 amps hour or 20,400 milliamps hour. So this is how the battery pack systems are connected in both in series and parallel based on the load application point of view. If you take in 2-wheeler, 4-wheel, basically the load will be max more than 12.6, sometimes 36 volt or 42 volts. So based on that, you have to connect the batteries in both in parallel and series. So not only we are using cylindrical kind of batteries, we can see the prismatic types of batteries also used in the electric vehicles. Now before that, before moving to BTM system, let us see what is my C rating. So in this case, the C rating is very, very important. Okay, here, yeah. So the C rating is nothing but a capacity. It is a unit declare a current value which is used for estimating and designating the expected effective time of battery under variable charging and discharge ratings. Basically, the charging and discharging rate, the charging or discharging rate is specified by C. So basically, which is called a C rate. Okay, this is called a C rate. So what we call this is called a C rating. So in this case, you can see a battery having capacity of 1000 mAh and load has the capacity of 500 mAh. It means the load is 500 mAh and this battery is connected to a load of 500 mAh. It means this battery can be lost for 2 hours. Okay, this battery will last for 2 hours, and same if we're using same battery connection for a load of 1000 mAh, this is called as 1C. So which the battery will last for 1 hour. So in this case, 2 hours, which is nothing but 0.5C. So this is called as 0.5C. And the same battery, if we am using for a load of 2000 mAh, that means within a half an hour, the battery will get dried, which is called as 2C. It's called 2C rating, 1C rating. And similar manner, if I am using the load with a capacity of say 5000 mAh, so 5000 mAh, that means how to find this? Just divide the load by the battery specification. So 2000 by 1000 is nothing but 2. It's called 2C. Similarly, 5000 by 1000 is called 5. So in this case, it is called as 5C rating. So C rating is the very important parameter. So based on the C rating also, the amount of heat generation also increases. So basically, when C rate increases, when C rate increases, then heat generation also increases. the heat generation, which is normally we use the symbol QG, this heat generation rate will also increase as the C rate keeps on increasing, and this heat generation rate increases, and depends upon the load. Okay, when we are using the 1000 load at a time with the capacity of battery of 1000 mAh, so it is called 1C. When loads keeps on increasing, the C rate will also increases. When load decreases, then the C rate will also decreases. So in this case, this heat generation rate depends upon C rating. So please try to understand the C rating is one of the important parameter while designing the battery pack systems. Now, next, let us see what is my thermal runaway. In second slide, we have seen the electric scooter catching a fire because of this thermal runaway. The term thermal runaway is nothing but a condition in which a battery catches fire due to rapid heat propagation, due to rapid heat generation from one cell to another cell, one damaged cell to another cell. So basically, a battery pack consists of a lot of batteries connected in both series and parallel. When the thermal propagation happens in one battery, it also affects the neighbor batteries. It will transfer the heat to the neighbor battery. So the thermal propagation keeps on increasing. So finally, the total battery pack system catches fire. Okay, fine. For if you want, the desirable operating temperature for batteries is around 15 to 35 degrees Celsius. 15 to 35 degrees Celsius. But so we know that as C rate increases, that means the amount of power that I'm sending is increasing, right? The amount of power that I am sending is increasing. So basically, we know that the heat generation, the amount of, if the C rating keeps on increases, that means I am transferring the more power, right? I am transferring more power. So more the power, more the resistance, right? More the resistance, that means the more the electrons are flowing. So more the internal resistance, more the heat transfer. This leads to the more heat transfer. So in previous slide, we have discussed C rating. So when I using the higher C rating, then the more heat will be transferred, more heat will be generated inside the batteries. Now, okay. Now at 80 degrees Celsius, okay, what happens at 80 degrees Celsius in batteries? When battery attains at 80 degrees Celsius, this solid electrolyte interface layer or the negatively charged anode starts to decompose. So basically, a battery consists of both anode and cathode, right? But the interface layer of the negatively charged anode starts to decompose at 80 degrees Celsius. This is the starting point of thermal runaway. And when a temperature increases to say 100 to 120 degrees Celsius, then the electrolyte breaks down into exothermic reaction. So I hope you know, guys, you know that what is my exothermic reaction. So exothermic reaction is a reaction which produces a lot of heat during the chemical. So battery, what is happening is the battery, it's simply a chemical reaction, right? So this chemical reaction increases the heat. Okay, so here the heat will increases. It will release the more heat. And during 120 to 130 degrees, this separator melted down, and more heat is generated. So you can see there is a separator, right? We are discussing separator. The separator is the plastic membrane which is separating the anode and cathode electrode, right? This started melted. So this both the anode and cathode is meeting. So it creates the internal short circuit. So what's in short circuit? More heat generation. So after at 150 degrees Celsius, now the cathode, the positively charged cathode, begins to decompose and produces oxygen. So we have gases, we have oxygen. So it is enough to produce the fire, right? So this cathode layer produces oxygen, and during the exothermic reaction, it releases more gases. And this here we have gas and oxygen. When temperature reaches 180 degrees Celsius, the thermal runaway starts. Though the cell becomes thermally unstable and the condition of thermal runaway is reached. So this battery catches a fire at 180 degrees Celsius. So just understand, at 180 degrees Celsius, the thermal runaway starts. So even a single battery can start a thermal runaway. So it will transfer heat to the neighbor battery. So the fire keeps on increasing. And so how a single battery start propagation? That is a system called battery management system. Battery management system, what it's do is it will transfer the equal amount of power to the batteries. So when there is only one battery is generating heat, that means the internal resistance is with respect to the single battery. So more heat will generate. That's called thermal propagation with a single battery. Now this thermal runaway can take place within a 10 seconds. Okay, within a 10 seconds, this heat propagation may starts based on the load and battery during the charging and discharging behavior. And in this case, the amount of heat generated, it will be in the order of 10 power 7 watt per meter cube. The heat generated is the in terms of 10 power 7 watts per meter cube. So the desired operating temperature range of the battery is 15 to 35 degrees Celsius. Even in cold climate conditions, we have to heat this battery to attain this 15 to 35 degrees Celsius. We need some mechanism to heat the batteries in cold climates. In cold climate condition, even the battery might reach to C0 or minus 10 degrees Celsius. In such cases, we have to heat the battery by using some mechanisms like thermoelectric heater or heating coils like that. Okay, this is the main reason of the thermal runaway. This is the process of thermal runaway. And when a system reaches the thermal runaway condition, you can see what happens. What is happening? A battery catching a fire, so the total electric scooter gets fired because of thermal runaway. So because of thermal runaway only, this battery is catching a fire. So improper heat distribution, more heat propagation, more heat generations, which leads to thermal runaway. So we need some systems to maintain the temperature of the battery that we're going to discuss in coming slides. And here, which is called, now let us see battery thermal management system. So this is the system which is going to maintain the temperature of the battery. And here it is recommended that maximum temperature difference inside the battery pack does not exceed 5 degrees Celsius. That means the delta T, it should be less than 5 degrees Celsius, okay, or less than or equal to 5 degrees Celsius. Okay, so here, what's been a maximum temperature difference between battery to battery? A battery pack consists of lot of battery, right? What's been battery pack? It consists of lot of battery. So the temperature difference between the battery to battery should be limited to 5 degrees Celsius. Okay, so we know that the battery thermal temperature varies due to the internal heat generation during and charging and discharging process. So this uneven temperature distribution affects it will age the battery. That means it reduces the life cycle, and also it affects the power capacity. That means it affects the cell performance. It reduces the power capacity due to the internal resistance. So due to the internal resistance, it affects the power capacity. So two things, one is called aging of batteries and power capacity. Okay, it reduces the power capacity of the battery pack systems. So these are the main drawbacks of the battery. And so it is recommended that the maximum temperature difference inside the battery pack should not exceed 5 degrees Celsius. So to maintain a temperature, there is a system which is called as battery thermal management system is necessary to maintain the battery temperature in the desired range, and it plays the major role in the battery pack life and its overall performance. So we need some system called as battery thermal management system, and this system is used to maintain the temperature of the batteries. Now let us see the different types of battery thermal management systems used right now. So where there are different media used for the cooling the battery. One is air and liquid. Okay, so so we know that liquid has the very good thermal conductivity compared to air, but handling of air is a little bit easy and is less in weight compared to liquid. So most of the engines are used in air cooling mechanism, and even liquid cooling, the heat transfer is very efficient compared to air, because liquid has very good thermal properties like thermal conductivity compared to air. And in air, we can basically classify natural convection and forced convection. So I hope you guys know what's natural convection, forced convection. You might study in your bachelor's course, heat and mass transfer or heat transfer. So based on the different techniques like optimization technique, like type of battery layout and the airflow channel arrangement. So like which one should be inlet and which one should be outlet. We have to create a duct-like structure, and there are various optimization techniques like the spacing between the batteries, and the parameters like velocity, type of air, and the flow rate and flow arrangements and the space between the batteries. There are a lot of techniques which is to be optimized, and cooling fan placement. So if it is a forced convection, we need some mechanism like it's maybe a fan or blower, a pump, like our compressor, right? So we need some mechanism which consumes less power. So this is called as active system, and we are using the natural convection, which is called passive system. So active system in the sense, if you're using the external device, like if you're using the electrical energy consuming device to achieve this BTMS system, that is called active methods. So passive method, we are not using the any additional energy consuming device, that is called passive mechanism. That means of by natural convections, and forced convection means our active system means we're using the electrical energy or any energy consuming device to achieve this cooling method is called active systems. And under liquid cooling, there are different types available, like immersion type. You can see immersion type cooling, and indirect like immersion cooling, like just immersing the battery with proper geometries, like you can use cold plates and water jackets and heat pipes. So in heat pipe, which is called a phase transfer mechanism, right? A heat pipe is a phase transfer mechanism. Basically, you might see in the heat pipe in the laptops. The laptop, the heat, one end of heat pipe is attached to the processor, where other end is attached to the heat sink with a fan. So inside the heat pipe is basically a closed system which consists of liquids with the low boiling point inside the heat pipe. So one end is attached to the heat producing device, the another end is attached to the heat rejection device. Like basically in laptop, it is attached to the processor, the other end is attached to the fins or the heat sinks. So you can also use heat pipes for the cooling methods. And you can also use PCM. PCM is nothing but phase change materials. You can also use phase change material. Like what's been phase change material? Like for example, you take in wax, a candle, right? Let us take in candle, which changes its phase by absorbing heat. When I apply heat to the candle, what happens? It changes the phase from solid state to liquid state, right? It absorbs heat by transferring its phase. That's called liquefations. And vice versa. And this liquid will be converted to solid by releasing the heat. If the candle releases heat, this liquid will be converted to solid. That's called solidifications. So by using the PCM at the by immersing the battery in the PCM, also the PCM will absorb heat from the battery by means of phase transfer mechanisms. And you can also see material composition, because the PCM has some drawback, like it has very less thermal conductivity. So by adding some nanoparticles and metal additives or like foams or fibers, we can like nanoparticle like graphene, metal oxide, metal powders, we can increase the thermal property. There are a lot of literatures available by improving the thermal property of the PCM. Now, in this case today, it is very big topic. Now, in this case, we are going to focus on the air type of cooling. And here, you can see there are different applications of the convections. I want you guys to tell which one is the forced convection, which one is the natural convection. Just put in the chat box. I hope you know what we have studied, what's been natural convection, forced convection. I will explain. This is nothing but a graphics card, and this is the processor. And this, we know, a two-wheeler engine is the heat produced by the bulb, and the heat produced by the human body, and heat produced in the projectors. So these are some of the examples taken for the convection. Just put it in the chat box, which one is belong to the natural and forced convections. Yeah, the processor. Forced convection by CPU, very good, exactly, Mohit. The forced convection by CPU cooler. So in CPU, we are using the fan, which releases the heat from processor. Yeah, processor is forced convection, exactly. And fins is natural, one with fan is forced. So IC engine is natural, exactly. Yeah, great guys, very good observations. So in electric vehicle, in an engine body, you can see there is a fins, right? Engine is natural, exactly. Human bodies are natural, great. Very good answers. Yeah. Engine, bulb, humans are natural convection. Engine is for okay. Forced convection is processor, projector. Exactly, Prasad. Thank you. Great, great guys. So in project you might have seen there is a fan process. So nowadays you can see every college. So most of the guys are from college side. We are having a project like what is called modern classroom, right? Like we're having the projector where you can see this is the air exhaust vents. Inside this, there is a fan running. That's why your teachers might be advised don't switch off the projector directly. Wait for a few minutes so that it will send the heat outside, right? So you can see in a projector or induction stove, there is a fan presented, even in CPU. So this is called, those are called as forced convection. This is the graphics card. You have to send some air to cool this graphics card. This is called fin-like structures. And the heat which is dissipated from the human body is called as F, natural convection. Okay, but if you are, it depends upon the situation. If you are sitting under the fan, basically it is a forced convection. We are pushing the air over our body, which will absorb the heat from the body, which is called a forced convection. And if you take it engine, so let us say the vehicle is moving at a speed of 40 kilometers hour. We know the Newton's law. We have the air passing at the velocity of 40 kilometers hour. Basically, it is natural convection, and since we are moving the vehicle, we are not using external device, right? So which is also called to be natural convection. And a bulb, we know that the bulb will produce a heat. Okay, so the air which is having contact with the bulb will keeps on heating, and this air goes away and cold air comes into the contact, and this is called as there is separation of separation of air in temperature. Even in AC room, you might see there is separation of air, right? So you can see the air with less temperature will be at bottom, air with higher temperature will be at top due to the density variation. This is called as air stratifications. Okay, great examples. Yeah, thanks you guys. Thanks for your response. Now, so these are only some of the examples that I have listed. You can see a lot of examples are available. Even you can take fan and energy, like even I am using a laptop. Inside the fan, there will be some fan. Now I'm using, there is a bulb. It's also natural convection if I am not using the fan. But if you are in air conditioning, like this kind of forced convection, we are pushing the cold air, right? Now, next, let us see. So before moving to the cooling methods, I'm going to recall the simple fundamentals that you have learned in the bachelor's degree. Like maybe in third year, you have learned the heat transfer subject, which is called as Newton's law of cooling. This is called convection law, right? You guys have learned this law in convection law, like Fourier's law of conduction. For conduction, you might have learned Fourier's law, and for convection, you have there is law called Newton's law of cooling. So Newton's law of cooling is nothing but a heat transfer is proportional to the temperature difference between a surfaces in which heat is transferred. Okay, so for example, you can see there's a cup of coffee where heat is transferred from the coffee to the surroundings, right? So now here the A is nothing but surface temperature. Okay, the surface temperature in which heat is transferred. So in this case, the surface temperature might be the cup. Maybe top surface there is surface temperature. Here there is a surface temperature. So here the heat will be transferred from conduction. Then after the convection, right? From coffee to the cup will be the conduction heat transfer. From the cup to the surrounding air is called the convection heat transfer. So now from Newton's law of cooling, we know Q is equal to HA delta T, where A is the surface area in which heat is transferred, and delta T is the temperature difference between the two surfaces in which it is transferring. And H is the important term, which is called as heat transfer coefficient, which is written by watt per meter square Kelvin. The amount of heat transfer per unit area per unit degree rise is called heat transfer coefficient. And this is called heat transfer coefficient. We are discussing what is H in coming slides. Now, before moving to going to revise some dimensionless number, which is very important in the case of forced convection. So one is called Reynolds number, right? And we have used this Reynolds number in most of the subject like fluid mechanics, heat transfer, gas dynamics. So which is nothing but rho U L by mu, where rho is the density of the fluid, U is the velocity of fluid, L is the length of the plate in which fluid is flowing in terms of external flow, In terms of internal flow, it is called as D. D is diameter of the pipe in which fluid is flowing, and mu is the viscosity of the fluid. So basically, this rho by mu is nothing but a property relations, in which you can also write as UL by nu, right? But nu is the kinematic viscosity, which is nothing but ratio between the absolute viscosity to the density of the fluid. So basically, the laminar flow is nothing but when Reynolds number is less than 2300 in terms of internal flow. Okay, in terms of internal flow, sorry for the mistake. In terms of internal flow, it should be less than sorry, it's correct only. Here it is written as here. So the Reynolds should be less than 2300 for internal flow, and for external flow, it should be less than 10 power 5. Okay, in terms of external flow, it should be less than 10 power 5. And similarly for turbulent flow, the Reynolds number should be greater than 4000. So in between is called transition flow. And for external flow, the turbulent should be more than 5 into 10 power 5. Right? You have to so because based on the types of flow, it may be internal or external or turbulent flow or turbulent or laminar, you might have used there is various correlations available in the data book like Nusselt number correlations. So here, let us see what's been Nusselt number. So Nusselt number is nothing but a ratio between the conductive heat transfer to the convection heat transfer to the conductive heat transfer. Basically, mathematically, it is written as HL by K. Okay, HL by K. That is K by L is K by thickness. Okay, L by H. So convection heat transfer K is when convection heat transfer is dominating, the Nusselt number will be high. When conduction heat transfer is dominating, then Nusselt number will be less. In most of the case, like application like conjugate heat transfer, we have both conduction as well as convection heat transfer, right? So Nusselt number denotes the increase in heat transfer through a fluid layer, which is called convection, related to the conduction heat transfer. When a fluid is motionless, there is no motion means, then what happens? So the conduction is dominating. Okay, there is no bulk motion, that means no convection heat transfer. In such cases, the conduction is dominating. In where Nusselt number will be the almost equal to 1. When there is a bulk motion, when convection term is dominating, then convection will be higher than the 1. Okay, this convection will be higher than. So this Nusselt number correlation is very important. Now let us see, there are different types of convections which you have studied. Forced convection, natural convection. If you are using actual device like pump or blower or a fan, that is called a forced convection. Here you can see there is a hot egg. So to cool this egg, I'm using some actual device like fan. So a cooling rate, so I'm increasing heat transfer. This kind of convection is called forced convection. But natural convection means the air, the surrounding air, you have contact with the egg cell, which just get heated. This hot air will move upside and the cold air will come back, right? This hot air will go upside, the cold air will come back, and this cycle repeats. But in this case, the heat transfer rate is less compared to the forced convection. So this is the difference between natural and forced convection. And here, I'm going to introduce the main term called the heat transfer coefficient. So in the convection heat transfer, the heat transfer coefficient is a very important term. And basically, this is not a property of fluid. Okay, it is experimentally determined parameter, and in which this H will depends upon variable parameters like a surface geometry in which heat is transferred. It may be a plate or pipe. It may be complex structures, and nature of the fluid motion, like a velocity. Nature of fluid motion may be like laminar or turbulent. Then properties of fluids, it may be a gas, it may be a water. It may be ethylene glycol, it may be oil, it may be like mercury, whatever it is. The property of fluid plays a major role because different fluid has different viscosity, right? Where viscosity plays the major role in oil heat transfer. And the bulk fluid velocity. Okay, the velocity is very important term compared to other term. When velocity increases, the heat transfer coefficient will also increases naturally. Okay, when velocity increases, the heat transfer coefficient will also increases. So basically, the heat transfer coefficient H will be in the range of 2 to 25 in free convection for gases. And for liquids, the range will be 10 to 100,000. 10 to 1,000 for liquids, because liquid has very good thermal property like thermal conductivity compared to gas. So the convection heat transfer will be higher for liquids. And similarly for forced convection, it is multiplied by 10. You can see 25 to 250. And for liquids, 50 to 20,000. And during boiling and condensation, during the phase transfer process, this H will be dominating, which is greater than thousands, like 2,500 to 1 lakhs. So these are different ranges, okay, based on the convection, like properties like fluid, type of fluid, bulk, velocity, and geometric profile. Now let us introduce the BTMS techniques. So in this case, here I have briefed. I'm going to discuss only about the air cooling. Since there is a limited time period, we're going to discuss air cooling. So this is nothing but battery pack systems. Okay, this is the one of the literature. So here you can see there are a lot of batteries connected, and this is the battery pack systems. So here this is the temperature distribution of natural cooling. So this is done by the CFD analysis, the CFD tool like ANSYS Fluent. Here you can see the natural convection of the heat from the battery to the surroundings, where you can see there are hot points at the center, right? Where the outer circumference of the battery pack system, the heat is less. Why? Since this battery having the contact with the surrounding air, where there will be convection heat transfer. So the outer circumference battery has less temperature compared to the center battery. So here at center we having the 52 degrees Celsius, where the outer case we have 47. So the delta T is almost 5 degrees Celsius. So this is without cooling process. Now let us see there is a temperature distribution by top inlet and bottom outlet. This we are having a duct-like structure. I'm sending the air from top direction and the like leaving the duct at the bottom direction. So what happens basically, the top surface would be getting cooled, right? The temperature of the top surface would be less compared to the bottom surfaces. This is the one mechanism which can be followed for the air-based BTMS systems. And here you can see the laterally inlet and outlet, like the inlet and out, they have changed the inlet and outlet pattern. So based on the pattern of the inlet and outlet, the temperature distribution also varies. In this case, you can see there is the hot batteries, which is having temperature of 40, and here we have 29. So I think that like this is your inlet and this is your outlet, like lateral arrangements. There might be used some structure like duct-like structure like this. So they will send the air from this side and the air leave this side. Okay, so the air entering this battery pack will absorb a lot of heat. So when air moving to this side, mostly the air will be gets heated. That's why the battery is not cooled here. So by changing the air arrangements, also we can study these things can be studied using the CFD software. And this is also one of the case study where by changing the space between the batteries, here you can see there are 3 cases where there is no space between the batteries. So in second case B, the space between the batteries was maintained at 2 mm, and third one is called the space between the batteries 4 mm. So if you compare to B and C, so even though spacing between the batteries is high, the third case, so third case is even though the spacing between batteries is high, but you can see the lot of hot points. So you have to optimize the distance between the batteries. Okay, you cannot increase the battery spacing, and also you cannot maintain any close contact structure. So there is a porous media, right? So you have to optimize the space between the batteries so that we can maintain the temperature uniform, not only the uniform temperature and also less temperature. So always remember that delta T should be always less than or equal to 5 degrees Celsius. Delta T. The delta T is the temperature difference between the batteries. So in this case, they have used this well spacing to study the temperature distributions. So likewise, you can see you can change a lot of parameters, like you can change the velocity. Okay, you can change the spacing. You can change the geometry of the battery pack systems. Okay, you can also, instead of air, you can also use some mechanism where you can also use some diffuser. The inlet might be you can also send inlet. You can insert some tubes pipe, like you can insert some tubes in between batteries, and there might be some small holes like diffusers. Likewise, you can change a lot of things using the CFD, because CFD has a lot of advantages. Instead of doing some experimentations or thermal modeling, you have to do simple geometry, and which you can analyze using the computation, using the computers. Okay, so CFD is a very important tool in terms of heat transfer or flow analysis. Now this is this one small thing which is done in the skilling. So here, okay. So this is the animation which is done using CFD tool in the skilling. So this is the difference between the battery pack system with cooling and without cooling for 1C charging. And here you can see, so this video, the left hand side video shows, you can see, the battery keeps on increasing, the temperature of the battery keeps on increasing without the cooling process. So initially the temperature was around 26.94 and finally the temperature is around 55.17. So this is the animation of the battery pack system, the temperature distribution of the battery pack system, which keeps on increasing. Now, what happens if I'm sending the air? Okay, I'm just sending the air from left hand side, right hand side. Okay, with a velocity of 5 meters per second. So what happens here? So even the temperature of the battery will increasing, but it is limited to 46 degrees Celsius. By a velocity of 5 meters per second, I can able to maintain temperature of 46. So the difference is 55 minus 46, almost 8 to 9 degrees Celsius, right? Almost 9 degrees Celsius differences. Okay. So by that, by changing the velocity or by changing the spacing between the fluids or by using the different flow mechanisms, you can study the temperature distribution of the battery pack systems. So I will play this video again. So this is the without cooling process, the temperature keeps on increasing due to the heat generation. And here you can see the temperature of the battery is also increasing, but due to the air velocity, here the inlet air temperature was made at 25 degrees Celsius and the velocity was 5 meters per second. So this is the one of the BTMS techniques by using the air is the cooling media. Now let us see one of the case study which was done by using like this was performed using the CFD tool and heat transfer analysis on heat generating battery using forced convection methods. Now, so here you can see the case study was taken as to perform the heat transfer analysis using ANSYS software for the cylindrical battery. Sorry. Yeah, for the cylindrical battery with the heat generation boundary condition. And here we have created an enclosure using air as the working media for the cooling the battery pack system. So here the battery pack we have taken as 7x3 batteries and the inlet temperature and velocity of air was maintained as 25 and 5 meters per second. And these are the properties of the battery taken from some literatures, the density, specific heat, thermal conductivity, and discharge rate. Here in this case, we have taken as discharge rate. And for heat generation, we have used the simple formula which is called V cross I. And we have taken the 18650 battery. So in this case, we have taken the 18650. So 18650 is the commonly used batteries like so 18650. In this case, the 18 is with respect to the diameter of the battery and 65 is with respect to the height of the battery. Now, so this is so basically in CFD, there are pre-processing and post-processing. In pre-processing, we are creating some geometry and we are then discretization. So discretization is nothing but splitting a surface into small surfaces to ease the computer for solving the problem, because the computer won't solve the partial difference equations. So that we are dividing surface into small surfaces in order to convert into linear algebraic equations. So it is the computer to solve the given engineering problems. And here you can see the geometry which was created using the ANSYS software, ANSYS Space Client, which is having 7x3 battery arrangement. This is your top view, front view, and side view. So totally we have 7x3, which is 21 batteries. And we have to give name selections in the meshing. So like we have taken this is the inlet and this is the outlet profile, and we have named this is battery wall. And even if you not assign the name for the enclosed the computational domain, the ANSYS fluent will taken as wall. Okay, you can go to the setup and you can check the boundary type of boundary. And this next pre-processing, we have to this is called discretization, mixing to capture the flow separation prism layers are provided around the battery wall. So around the battery wall, because this is the wall, okay, this is the wall in which a heat is transferred, right? So this heat is transferred between the battery and the fluid media. So we have to create the structure, like it's called insulation layer, and around the battery wall. And here the element size was maintained at 2 mm, and the type of volume is called tetra CFT, and total number of elements is like around more than 1.85 lakhs is the total number of filament. And this meshing was performed using the CFT tool only. Now next, solvers. Okay, and what are the settings that we have given the solvers? Like basically this is a pressure based solver. We have to decide whether pressure based or density based on the Mach number. So we know Mach number is nothing but a speed of the fluid by speed of the sound. And type of model you have to select based on your experience or knowledge of thermal modeling. You have to select either K epsilon or any other models. And we have switched on the energy equation since the heat transfer is working. And you have to assign the fluid material. For the computational domain, we have used air. We have chosen the air as from the fluid database itself. And we have defined the material for battery since it is not available in the fluid database. You have to define some user-defined material like battery. And we have to assign the properties like density, specific heat, and thermal conductivity, so on. And boundary conditions. So we have used velocity inlet, boundary condition, pressure outlet condition, and wall for cylindrical walls and the computational domains. Then we have initialization problems. Basically, initialization is that like find the initials, like giving key to the vehicle. So user inputs the initial values of the parameters. So next, post processing. So we have and this is done for the transient analysis for varying step size. This analysis for done for around 400 seconds times. So this 400 seconds, this for the end results take more than 10 hours. Okay, for various steps, take more computational time steps. This computational time depends upon the mesh size as well and the complex of the engineering problem. And this is the streamline which shows the velocity profile, velocity streamline. And here this is the left side is the inlet condition, and this is your outlet. This is the air moving the body. And here you can see the streamlines and the air getting inside the batteries as well. You can see the air is getting inside the space between the batteries. And this is the cut section view. Okay, this is the cut section view. And here you can see the final temperature contour. And here you can, since this is your inlet velocity, okay, and this is your inlet velocity, and this is your outlet. So this is your outlet, okay. And here the velocity was maintained at 5 meters per second. And here you can see the first battery gets cooled compared to the last battery because the air is moving from left to right hand side, and the inlet temperature of air is maintained at 25 degrees Celsius. So the air which gets contact with the first battery, it absorbs heat. So when I move to this side, the air temperature is almost near to, like you can see, near to 350 Kelvin. So the last battery is not cool. So by changing the flow parameters like flow patterns, you can do some analysis similar to this by using the CFT tools. And this is the cut section view, front view. And here you can see the cut section view of the top view. And here in similar manner, you can see the velocity vector and the temperature contour. Now here you can see the animation of the temperature. Yeah. So this is the animation of the temperature contour. So here you can see that the temperature of the battery keeps on increasing. So the air is moving from the left hand side to right hand side. So this is the one of the project done in the Skillink by using the CFE tool. And similar to this, you can do a lot of things, battery techniques, even not using the air. You can also use the liquid as the coolant. So if you're using liquid as the coolant, but you cannot use the direct contact with the batteries, it will create a short circuit, right? So you have to use a cold plate kind of structure, and you can do some such kind of analysis. Maybe in future we'll be discussing about liquid-based BTMS systems. And here, this was done for the 5C discharging rate. So you can see the more amount of heat is discharged. The maximum temperature is around nearest to 110 degrees Celsius, because this is for 5C rating and with a velocity of 5 meter per second, the average velocity of 5 meter per second. So here the average velocity is 5 meter per second. Now, similarly, we have done the for single battery, for single unit with 1C rating. So in this case, the air is moving from the right hand side to left hand side. And here you can see the battery temperature keeps on increasing. The maximum temperature of the battery is about 340 Kelvin. Okay, the average temperature was maintained at 5 meter per second. So initially we have given the less time steps so that we can see there is less movement, the temperature. So after that we have gradually increased the time steps. Now we can see the temperature keeps on increasing. So here we are using the air as the working fluid. I think when able to see the animation, right? Balaji's animation is visible.
Yes, sir, it's visible.
Yeah, thank you. So you can see the temperature keeps on increasing. So maximum temperature is at 340.38 Kelvin, even after using the air as the cooling media with the 5 meter per second. So by changing the parameters like in the temperature of the air or velocity of the air, a type of the cooling media, by improving the thermal conductivity of the air, basically the thermal conductivity of the air is very less, right? Even air can be used as the insulation material because of very low thermal conductivity. So instead of using air, we can also use different cooling medias, and we can see same similar kind of analysis using the software like CFD, CFD Fluent. So CFD Fluent is one of the tool available in the ANSYS software. And this is my this are the reference for this my PPT presentation. Okay, thank you all for your participation.